two particles separated by the entire width of the observable universe, 14 billion light-years of empty space between them. You disturb one particle, and the other responds instantaneously, not in 14 billion years, not at the speed of light, instantaneously. This isn't science fiction. This is quantum entanglement, and it's been proven in laboratories thousands of times. Einstein called it spooky action at a distance. He believed it revealed a fundamental flaw in quantum mechanics. He was wrong. The universe, it turns out, is far stranger than even Einstein imagined. What if I told you that every particle that has ever interacted in the history of the cosmos might still be connected? What if the fabric of reality itself is woven from invisible threads of quantum correlation? What if space and time are not what separates things, but what emerges from these quantum connections? Today, we journey through evidence that challenges everything we thought we knew about the nature of reality itself. Prepare yourselves, we begin. In 1935, Albert Einstein sat in his Princeton office with a problem that wouldn't let him sleep. Quantum mechanics, the revolutionary theory describing the behavior of atoms and particles, predicted something that seemed impossible. Two particles could become linked in such a way that measuring one would instantly determine the properties of the other, regardless of the distance between them. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper designed to expose what they believed was quantum mechanics' fatal flaw. They proposed a thought experiment. Imagine a particle that decays into two smaller particles flying apart in opposite directions. Quantum mechanics said these particles remained in a superposition where neither had a definite spin until measured. But the moment you measured one particle's spin, the other particle would instantly have the opposite spin. The problem? This seemed to require information traveling faster than light, violating the cosmic speed limit established by Einstein's own theory of relativity. Nothing, Einstein insisted, could travel faster than light. Not particles, not energy, not information. Einstein believed this paradox proved quantum mechanics was incomplete. There must be hidden variables, predetermined properties the particles possessed all along. The particles weren't really connected. They simply carried instructions from birth, like identical twins separated at birth who nonetheless make similar choices. For 3 decades, this remained a philosophical debate. Quantum mechanics worked perfectly for calculations, but did it describe reality? The question seemed impossible to answer experimentally. Then, in 1964, a physicist named John Stuart Bell, working at CERN, made a breakthrough that would change everything. Bell proved mathematically that Einstein's hidden variables and quantum entanglement made different, testable predictions. Bell's theorem is elegant in its simplicity. If particles carry hidden instructions, their correlations must obey certain statistical limits. But if quantum entanglement is real, if particles genuinely remain connected, those correlations can violate those limits. The implications were staggering. For the first time in history, humanity had a way to test the fundamental nature of reality itself. We could determine whether the universe operates on classical principles of locality and realism, or whether quantum mechanics' stranger vision is correct. The test would require measuring entangled particles at different locations, carefully choosing what properties to measure at each location, and comparing the statistical correlations. If the correlations exceeded Bell's limit, Einstein was wrong. The universe really does permit instantaneous connections across space. In 1982, French physicist Alain Aspect and his team performed the decisive experiment. Using specially prepared photons, they created pairs of entangled particles and sent them flying apart. At the last possible moment, random number generators determined what property each photon would be measured for, ensuring no hidden signal could coordinate their behavior. The results were unambiguous. The photons showed correlations exceeding Bell's limit by a wide margin. Quantum entanglement was real. But here's where it gets strange. The measurements showed perfect correlations, yet there was no time for light to travel between the measurement devices. The second photon knew how the first had been measured, despite the absence of any possible signal. Aspect's team verified their results through thousands of repetitions. Other laboratories around the world repeated the experiments with increasingly sophisticated technology. Every single test confirmed the same impossible conclusion. Quantum entanglement remains connected regardless of distance, responding to measurements on their partners faster than light could travel between them. The universe, apparently, doesn't care about the speed of light when it comes to quantum correlations. But this represents just one piece of a much larger puzzle hidden in the quantum foundation of reality itself. Scientists didn't stop with Aspect's tabletop experiments. They needed to know, does entanglement persist across truly cosmic distances? In 2017, Chinese researchers using the Mitzias satellite created entangled photon pairs and sent them to ground stations separated by 1,200 kilometers. The photons remained perfectly correlated. The invisible quantum connection stretched across a distance where light takes 4 milliseconds to travel, yet the correlation was instantaneous. The team led by Zhao Pan measured over 1 million entangled photon pairs. Statistical analysis showed correlations that violated Bell's inequality by more than 11 standard deviations. In scientific terms, this is overwhelming proof. The odds of this occurring by chance are less than in trillions. But distance is just one dimension. What about time? In 2013, researchers at the Hebrew University of Jerusalem demonstrated something even stranger: entanglement swapping across time. They created entangled pairs of photons, but here's the twist. They measured and destroyed the first photon before its entangled partner even existed. They created photon A entangled with photon B. They measured photon B, destroying it. Then they created photon C and D, entangling them. Finally, they performed a special measurement linking photon A to photon C. Despite photon B being destroyed before photon C and D existed, the final measurement showed that photons A and D became entangled. Think about that. Two particles became quantum mechanically connected despite never coexisting in time. The implications challenge our understanding of causality itself. Entanglement wasn't limited to individual photons. In 2018, researchers at the University of Glasgow created entanglement between a photon and a collective vibration of billions of atoms in a silicon device. The photon was measured 16 kilometers away, yet its quantum state remained correlated with the atomic ensemble. Then, in 2021, two separate teams created entanglement between small diamonds visible to the naked eye. These weren't individual particles, but macroscopic objects containing trillions of atoms. The diamonds, separated by different rooms, displayed quantum correlations that shouldn't exist in everyday objects. The boundary between quantum and classical worlds was dissolving. If diamonds could be entangled, what else could be? The most remarkable evidence comes from space itself. When high-energy cosmic rays collide with Earth's atmosphere, they create showers of thousands of particles cascading towards the surface. Physicists studying these cosmic ray events found something unexpected: statistical patterns suggesting many of these particles remain entangled with each other and potentially with their source. Consider what this means. A cosmic ray generated in a supernova billions of light-years away strikes our atmosphere. The particles it creates spread across kilometers of sky, yet they carry quantum correlations linking them together and possibly back to the stellar cataclysm that birthed them. The universe might be filled with invisible quantum threads connecting distant events across space and time. But this represents just one piece of a much larger puzzle hidden in the quantum foundation of reality itself. Scientists didn't stop with Aspect's tabletop experiments. They needed to know, does entanglement persist across truly cosmic distances? In 2017, Chinese researchers using the Mitzias satellite created entangled photon pairs and sent them to ground stations separated by 1,200 kilometers.
the photons remained perfectly correlated. The invisible quantum connection stretched across a distance where light takes 4 milliseconds to travel, yet the correlation was instantaneous. The team led by Xiaowei Pan measured over 1 million entangled photon pairs. Statistical analysis showed correlations that violated Bell's inequality by more than 11 standard deviations. In scientific terms, this is overwhelming proof. The odds of this occurring by chance are less than in trillions. But distance is just one dimension. What about time? In 2013, researchers at the Hebrew University of Jerusalem demonstrated something even stranger: entanglement swapping across time. They created entangled pairs of photons, but here's the twist.
They measured and destroyed the first photon before its entangled partner even existed. They created photon A entangled with photon B. They measured photon B, destroying it. Then they created photons C and D, entangling them. Finally, they performed a special measurement linking photon A to photon C. Despite photon B being destroyed before photons C and D existed, the final measurement showed that photons A and D became entangled. Think about that. Two particles became quantum mechanically connected despite never coexisting in time. The implications challenge our understanding of causality itself. Entanglement wasn't limited to individual photons. In 2018, researchers at the University of Glasgow created entanglement between a photon and a collective vibration of billions of atoms in a silicon device. The photon was measured 16 kilometers away, yet its quantum state remained correlated with the atomic ensemble. Then, in 2021, two separate teams created entanglement between small diamonds visible to the naked eye. These weren't individual particles, but macroscopic objects containing trillions of atoms. The diamonds, separated by different rooms, displayed quantum correlations that shouldn't exist in everyday objects. The boundary between quantum and classical worlds was dissolving. If diamonds could be entangled, what else could be? The most remarkable evidence comes from space itself. When high-energy cosmic rays collide with Earth's atmosphere, they create showers of thousands of particles cascading toward the surface. Physicists studying these cosmic ray events found something unexpected: statistical patterns suggesting many of these particles remain entangled with each other and potentially with their source. Consider what this means. A cosmic ray generated in a supernova explosion billions of light-years away strikes our atmosphere. The particles it creates spread across kilometers of sky, yet they carry quantum correlations linking them together and possibly back to the stellar cataclysm that birthed them. The universe might be filled with invisible quantum threads connecting distant events across space and time. But this represents just one piece of a much larger puzzle. The evidence extends beyond particle physics into the realm of cosmology itself. Stephen Hawking discovered in 1974 that black holes aren't perfectly black. They emit radiation through quantum effects near the event horizon, slowly evaporating over eons. But this created a paradox. If a black hole evaporates completely, what happens to the information about everything that fell in? In quantum mechanics, information cannot be destroyed. It's a fundamental principle. But Hawking radiation appeared to carry no information about the black hole's contents. The information seemed lost forever, violating quantum mechanics. The solution, proposed by Leonard Susskind, Juan Maldacena, and others, involves entanglement. The radiation emitted from a black hole remains quantum mechanically entangled with the material inside. As the black hole evaporates, the entanglement transfers the information back out, encoded in subtle correlations between the emitted particles. This means every photon of Hawking radiation carries quantum connections to the black hole's interior. The information isn't lost, it's preserved through entanglement, spread across the radiation in a scrambled but recoverable form. In 2013, physicists Juan Maldacena and Leonard Susskind proposed something revolutionary. What if entanglement and wormholes are the same thing? Einstein and Rosen had proposed in 1935 that quantum entanglement might be explained by Einstein-Rosen bridges, microscopic wormholes connecting particles.
Maldacena and Susskind revived this idea with a twist. They suggested that every pair of entangled particles is connected by the non-traversable wormhole through the fabric of space-time itself. The equation ER equals EPR connects Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, quantum entanglement. It suggests that quantum entanglement isn't some mysterious force acting across space, but geometric connection through space itself. This radical idea means space isn't what separates entangled particles. Space is what emerges from their quantum connections. Distance is an illusion arising from the complex web of quantum entanglement threading through reality. The evidence grows stranger. Theoretical work on black holes revealed the holographic principle. All the information contained in a volume of space can be encoded on its boundary, like a hologram. This principle connects directly to quantum entanglement. Researchers discovered that the amount of quantum entanglement between a region of space and its surroundings determines the geometry of that region. More entanglement creates more space. Less entanglement means less space. Calculations by Mark van Ramstonk and others showed that if you gradually reduced entanglement between regions of space in theoretical models, space itself would fragment and tear apart. Space-time, it appears, is woven from quantum entanglement. The most remarkable discovery involves the mathematical relationship between quantum entanglement and Einstein's equations for gravity. They're deeply connected, suggesting gravity itself emerges from quantum entanglement patterns. But the evidence extends beyond theoretical physics into observational cosmology. During the first fraction of a second after the Big Bang, a period called cosmic inflation, space expanded faster than light. This rapid expansion separated regions of the universe that had been in contact, potentially stretching entangled particles across billions of light years. Calculations suggest the cosmic microwave background radiation, the oldest light in the universe, might carry signatures of quantum entanglement from inflation. Particles that emitted this radiation 13.8 billion years ago may still be entangled with each other and with the quantum fluctuations that seeded galaxies. If true, the entire observable universe is threaded with quantum correlations dating back to its first moments. Every galaxy, every star, every atom might carry invisible connections to the cosmic web of entanglement established at the dawn of time. The evidence extends beyond individual particles into the realm of cosmic structure itself. What does quantum entanglement actually transmit? This question troubles many people. If entangled particles coordinate their behavior instantaneously, doesn't that allow faster-than-light communication? The answer reveals something profound about information itself. Entanglement doesn't transmit classical information. You cannot use it to send messages. Here's why. When you measure an entangled particle, you get a random result. Your measurement does affect the distant particle, but you cannot control what result you get, and you cannot know what the distant measurement found without classical communication traveling at light speed or slower. What entanglement preserves is quantum information, a deeper form of information about correlations and relationships between systems. It's information about the global state of a quantum system, not localized information you could use to send messages. This forces us to reconsider fundamental assumptions about what information means. Classical information is about bits, zeros and ones, definite states. Quantum information is about relationships, correlations, and potentialities that only become definite through measurement. Entanglement connects directly to quantum mechanics' deepest mystery, the measurement problem. Before measurement, entangled particles exist in superposition, having no definite properties. Measure one and both suddenly have definite states. But what counts as a measurement? What causes the quantum world to crystallize into definite outcomes? Some physicists, following the Copenhagen interpretation, say consciousness somehow collapses the quantum state. Others embrace the many worlds interpretation. Every measurement splits the universe into multiple branches where each possible outcome occurs. A third approach gaining traction involves decoherence and entanglement with the environment. When a quantum system interacts with its surroundings, entanglement spreads from the system to the environment, creating the appearance of collapse without any actual collapse occurring. The information doesn't disappear, it becomes distributed across vast entanglement networks, including air molecules, radiation, and observers. This perspective suggests measurement isn't special, it's just entanglement spreading outward, connecting the quantum system to larger and larger portions of the universe until the quantum correlations become practically irretrievable. The most ambitious theoretical framework connects quantum entanglement to the very structure of space-time. String theory, loop quantum gravity, and other approaches to quantum gravity increasingly suggest space-time isn't fundamental. It emerges from quantum entanglement patterns at the Planck scale, the smallest meaningful length scale in physics. Researchers like Brian Swingle have shown that the geometry of spacetime can be reconstructed from entanglement patterns using techniques borrowed from quantum information theory. Specific entanglement structures correspond to specific spacetime geometries. This means Einstein's curved spacetime, the fabric that gravity bends, might be a large-scale emergent phenomenon arising from quantum entanglement at microscopic scales. Gravity isn't a fundamental force, it's what you perceive when you don't have access to the complete quantum information about entanglement patterns. Recent work by physicists including Daniel Harlow and Patrick Hayden explores how entanglement entropy, a measure of quantum correlations, relates to the areas of surfaces in curved spacetime. The mathematics matches Einstein's equations in specific limits, suggesting deep unity between quantum mechanics and general relativity. Understanding entanglement isn't purely academic.
Multiple countries are building quantum communication networks using entanglement for unhackable encryption. China's quantum satellite network already operates across Asia. Europe and North America are developing similar infrastructure. These networks exploit a remarkable property. If anyone intercepts entangled particles, the entanglement breaks, immediately alerting both parties. You cannot eavesdrop on quantum communication without being detected. This makes entanglement-based quantum cryptography theoretically unbreakable. By 2030, major cities worldwide may connect through quantum networks, with entangled particles distributed by satellites and fiber optic cables, creating a global web of quantum-secured communication. Banks, governments, and research institutions are investing billions in this technology. But communication is just the beginning. Quantum computers use entanglement to process information in fundamentally new ways, potentially solving problems impossible for classical computers. Every quantum computer depends on entanglement. The more quantum bits you can entangle, the more powerful the computer becomes. Current quantum computers entangle dozens of qubits. Future machines might entangle thousands or millions. These systems could simulate molecular chemistry with perfect accuracy, design new materials, optimize complex systems, and crack currently unbreakable encryption. They achieve this power through entanglement, allowing quantum computers to explore many solutions simultaneously. Google's quantum computer achieved quantum supremacy in 2019, performing a calculation in minutes that would take classical computers thousands of years. IBM, Microsoft, and other companies are racing to build larger quantum computers with more entangled qubits. The implications extend beyond technology. Quantum computers might simulate the quantum entanglement patterns of the early universe, helping cosmologists understand how quantum fluctuations grew into galaxies. They might reveal whether consciousness involves quantum entanglement in the brain, testing theories proposed by Roger Penrose and others. Upcoming observatories might detect cosmic entanglement directly. The cosmic microwave background satellites planned for the 2030s will measure correlations between photons with unprecedented precision. If inflation created cosmic-scale entanglement, these missions might find statistical signatures violating classical limits. The James Webb Space Telescope and future instruments might detect entanglement signatures in distant galaxies. If quantum correlations persist across cosmic distances, light from entangled sources could show subtle patterns revealing quantum connections threading through space.
Ground-based experiments are testing entanglement over increasingly large distances. A proposed experiment called Space Quest aims to create entanglement between satellites orbiting different planets, testing whether quantum correlations survive in curved spacetime near massive objects like the Sun. These observations will test whether entanglement is truly unlimited, or whether gravity, curved spacetime, or other effects eventually break quantum correlations over cosmic scales. Perhaps the most speculative but intriguing possibility involves consciousness itself. Some researchers, including mathematical physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that quantum entanglement in brain microtubules might play a role in consciousness. The idea is controversial. Most neuroscientists believe the brain operates through classical physics, with neurons acting like digital switches. But recent evidence suggests quantum effects might occur in biological systems. Photosynthesis uses quantum coherence to transfer energy efficiently. Birds might use quantum entanglement in their compass sense for navigation. If quantum entanglement occurs in brains, consciousness might involve non-local quantum correlations across neural networks. Measuring brain activity might reveal quantum patterns distinguishing conscious from unconscious states. Anesthetics might work by disrupting quantum coherence in microtubules. Recent breakthroughs suggest we're approaching the technology needed to test these ideas, measuring quantum effects in living tissue at room temperature. The next decade may reveal whether consciousness has quantum origins or whether it emerges from purely classical neural computation. The most profound implications emerge when we consider what quantum entanglement reveals about reality itself. Before quantum mechanics, we assumed the universe consisted of separate objects with definite properties existing independently in space and time. Entanglement demolishes this assumption. Particles don't have definite properties until measured. They exist in superposition, simultaneously possessing multiple incompatible properties, and through entanglement, particles separated by cosmic distances form single quantum systems that cannot be meaningfully divided. This suggests a radical conclusion. The universe isn't made of separate things. It's a unified whole, a single quantum state encompassing everything. What we perceive as separate objects are local perspectives on this cosmic quantum state, regions where entanglement concentrates into structured patterns we interpret as particles, atoms, planets, and stars. John Wheeler proposed it from bit, the idea that physical reality emerges from information. Entanglement extends this. Reality might be it from qubit, emerging from quantum information and the entanglement relationships between quantum bits of information. The universe isn't a collection of objects in space. It's a network of quantum correlations, with space and time emerging from the pattern of entanglement threading through this network. Some physicists and philosophers propose the simulation hypothesis. We might live in a computer simulation created by an advanced civilization. Quantum entanglement provides intriguing evidence related to this idea. Quantum mechanics has a distinctive feature. The universe only computes definite outcomes when someone measures. Before measurement, systems exist in superposition, undefined states. This resembles how video games only render scenery when players look at it, saving computational resources. Similarly, entanglement creates correlations without storing information locally. An advanced simulation might use entanglement to minimize memory requirements, storing relationships rather than explicit values for every particle. The holographic principle discovered in black hole physics suggests the universe's information content scales with surface area, not volume. This resembles how computer simulations efficiently encode three-dimensional spaces using two-dimensional data structures. These parallels don't prove we're simulated, but they reveal the universe operates on principles surprisingly similar to optimal computational strategies. Whether this reflects the universe's quantum nature or hints at deeper truths remains unknown. Quantum mechanics introduces randomness into physics. Measurements yield unpredictable results, though the probabilities follow precise rules. Does quantum randomness create genuine free will, or is it merely replacing determinism with dice rolls? Entanglement complicates this question. Your brain contains approximately 86 billion neurons, each containing trillions of atoms. If quantum entanglement influences neural processes, your thoughts might involve quantum correlations connecting neurons across your brain and potentially beyond. Some researchers suggest consciousness might involve quantum entanglement between your brain and the broader quantum state of the universe. If true, your decisions might involve subtle quantum correlations with events throughout space-time. Your choices would be neither deterministic nor random, but influenced by the complex web of quantum information flowing through entanglement networks. This doesn't resolve the free will debate, but it opens new perspectives. Perhaps free will involves accessing quantum information through entanglement rather than simply responding to local stimuli. Your consciousness might tap into non-local quantum correlations, giving you access to information beyond classical physics's causal limitations. Every quantum experiment, every theoretical calculation, every piece of evidence points towards a singular conclusion. The universe is fundamentally unified. Not unified in the sense that everything is made of similar components, but unified in that separation itself might be an illusion. Quantum entanglement reveals that particles across the cosmos form interconnected systems. Space doesn't separate them, it emerges from their quantum relationships. Time doesn't order their interactions into past, present, and future. It represents the flow of entanglement spreading through quantum networks. We perceive a universe of separate objects because we only access local information. We measure particles in our laboratory without knowing about their quantum correlations with particles in distant galaxies. This limited perspective creates the illusion of separation, of space as empty distance between isolated things.
But the complete picture, accessible only through quantum information theory, reveals reality as a seamless web of correlations. Every particle that has ever interacted remains connected through entanglement. The cosmic web of quantum correlations stretches back to the Big Bang, connecting every atom in your body to events 13.8 billion years ago. You are not separate from the universe. You are a pattern in the universal quantum state, a local concentration of entanglement forming temporary structures we call consciousness, life, and matter. When you observe the distant stars, quantum correlations connect your observation to the stars themselves through the photons entering your eyes. The universe knows itself through these observation events, through consciousness emerging from quantum information processing in brains. You are the universe observing itself, quantum correlations folding back on themselves to create self-awareness. We began this journey asking whether Einstein's spooky action at a distance was real. Through decades of experiments, from Aspect's laboratory to Chinese satellites, from entangled diamonds to cosmic ray showers, the evidence became overwhelming. Quantum entanglement is real. But we discovered something far more profound than particles coordinating across space. We found evidence suggesting space itself emerges from quantum entanglement, that gravity might arise from entanglement patterns, that the universe is not made of separate objects, but forms a unified quantum whole connected by invisible threads of correlation. The current scientific consensus, supported by every quantum experiment ever performed, confirms entanglement violates classical intuitions about locality and realism. The universe permits instantaneous quantum correlations across arbitrary distances. Space does not separate entangled particles in any meaningful quantum mechanical sense. Yet mysteries remain. We don't fully understand how classical reality emerges from quantum mechanics.
We don't know if consciousness involves quantum effects. We cannot yet test whether cosmic scale entanglement threads through the observable universe. We are only beginning to explore how space-time geometry emerges from entanglement patterns. But we have learned this: reality is stranger, more unified, and more deeply interconnected than anyone imagined before quantum mechanics. The universe is not what it appears. Beneath the familiar world of separate objects in space and time lies a quantum reality of pure relationship, where every particle connects to every other through invisible bonds stretching across the cosmos. Perhaps this is what mystics meant when they spoke of universal unity. Perhaps they glimpsed through intuition what physicists discovered through mathematics and experiment. We are not separate beings in an indifferent universe. We are patterns in a cosmic quantum state, temporarily localized concentrations of information within the universal wave function. The implications ripple through physics, philosophy, and human self-understanding. They challenge us to reimagine our place in existence, to recognize the quantum threads connecting us to everything that exists, has existed, or will exist. The universe is vast, the mysteries are endless, the journey continues. But now we know, nothing is truly separate. Everything is entangled, and reality itself emerges from the invisible web of quantum correlations, threading through the cosmos.